Okay, we want to talk about line intervals. Okay, so as an example, we're going to do a density integral. Let's assume that we have some sort of a sheet of material here, and we have an x and y coordinate system imposed on it, and we know something about the density of the material in the sheet, okay? Now, that's not going to be the density function I'm talking about here, but I'll just explain to you how that might occur. And you're going to use, say, a laser cutter, a thin sheet of material, and you're going to cut a little strip of uniform width, very thin, out of this material, and you want to know what its mass is going to be. Well, you can take what you know about the density function in the plane and get a length density function. That's what this function is going to be. It's going to be very much related to the density in the plane. Basically, if you take the mass density in the plane and multiply it by the width of this thing at a point, you're going to get this length density. But let's just say, in some way or another, maybe as I've explained it, maybe in some other way, you know what the density of this material is, its mass per unit length at a given point x, y. Okay? So, let's say here is the path that you're going to use to cut this thing out, okay? Now, first thing we need to know is, well, the first thing we want to do is we want to partition this path. Now, this path consists of a set of parametric equations, a parametric equation x of t times I plus y of t times j, t being the parameter, x and y being the position in this plane. And this path extends from the t equals a position to the t equals b position. In other words, from x of ai to y of aj, we're going to get the vector to this point, okay? And then plug in b, we're going to get a vector out to this point, defining this point, and then all points in between. Okay. Now what we're going to do is we're going to partition. Maybe I should have written this down. I said it and it was implicit within our context, but let's partition the interval a less than or equal to t less than or equal to b. In the usual manner, you know, t naught is going to be a, and then the t1, t2, and so forth up to tn, which is b. Okay, on a typical subinterval corresponding to that partition, we're going to have an initial point somewhere in this curve and a final point in that subinterval. And we're going to have a sample point. Okay, well, let's take a closer look at that. Now, I had some blank space over here and decided that we really needed a little more explanation of this in case you're looking at it without the context that we had in class. So here again is a curve. And here's an interval, okay, from this point to this point, okay? Now, this vector here would be the vector from the origin out to the point x of ti minus 1 times the I vector plus y times t sub I minus 1 multiplied by the j vector, okay? And, you know, that corresponds to your parameterization of the path. And the other point would be the same, but evaluating at t sub I. So you would have these two positions on the curve. Then we're going to have some displacement, delta s sub I, from this point to this point. And that delta s sub I, of course, is going to have, can be broken down into a delta x sub I and a delta y sub I. So the delta y sub I plus the delta x sub I equals the delta s sub I. So, didn't write that down, but it's pretty well implicit. Now, the magnitude of delta s sub I is just going to be the hypotenuse of this triangle, so it's going to be delta x sub magnitude of the square root of your delta x sub I squared plus the magnitude of your delta s sub I squared plus the magnitude of your delta y sub I squared. Okay, and that should be pretty clear. Now, we want to make a real important connection here, and this is kind of a critical thing to understand. Your delta x, and I'm being careless with my subscripts, my delta x sub I is going to be approximately equal to x prime at my sample point t sub I star. Now t sub I star is just some value of t between the value that we have here and the value that we have here. Okay? So we just pick an arbitrary sample point and we take the derivative of x with respect to t and multiply that by our delta t. Well, that's just a differential approximation of the actual delta x sub I. So I say that the delta x sub I is close to x prime at t sub I star multiplied by delta t sub I. And the same thing for y sub I. Now, as we know, we're going to shrink our partition down in such a way, we'll shrink the mesh down, so that all our delta t sub i's approach 0, so that the approximation becomes more and more exact in the limit. Then we can say that our delta s sub I, the approximation of delta s sub I, is going to be the delta x sub I approximation plus the delta y sub I approximation. And the delta x sub I approximation times I, the delta y sub I approximation times j. So that the magnitude of delta s sub I is going to be approximately equal to, well, x prime squared plus y prime squared times delta t sub I, where I didn't have room to write it, but I wrote it over here, that the x prime squared, of course, is this x prime, the x prime evaluated at your t sub I star, and I left my stars off. They're over here. And this is where the delta s sub I comes from. So, come over here. Again, our delta s sub I is approximately equal to x prime t, this expression, which is identical to the expression we had here, except I factored out the delta t sub I. Then, our mass is our density times the length of that subinterval. The density is going to be evaluated at the sample point, okay? And I could, I didn't have room to label it, but our sample point might be somewhere, not exactly in the middle of the interval, but might be somewhere, anywhere in the interval, okay? And that would be our xy that we would get at t sub I. And maybe, to be perfectly clear, I can write that kind of small. That would be x of ti star I plus y of ti star j. So that would be our sample point. Maybe you can read that, but I read it to you, so hopefully you can write it down. We evaluate the density then at that point. Okay, so it's a density evaluated at x of ti star, y of ti star, the density at some point within the interval, and we multiply that by the length of that, of the part of the curve corresponding to that subinterval of our partition. Okay, so that would be our delta m, and again with great carelessness I left off a subscript there. Okay, so that would be our mass contribution of the interval. And then we replace the absolute value or the magnitude of delta s sub I with the expression that we obtained over here. And here is the expression for the mass of the ith subinterval. So what's our total mass? Well, as usual, we sum up all our delta m's, and that's going to be the sum of all the delta of x of t sub I star, etc. In other words, the sum of this expression. And, we could go from I equals 1 to n. And that's going to approach what integral? Well, our x of t sub i's, y of t sub i's become x of t's, y of t's. Again, this is a hand-waving explanation. I'm skipping a lot of stuff. But we're used to the fact that it does, and as I always urge you, make sure you understand why. And then the x prime of t sub I star becomes x of t sub I star, x prime of t, which I've just written as dx dt quantity squared, okay? Now that would be dx of t, so you'd have an x of t here, you have y of t here. But for compactness, I just wrote it dx dt squared, dy dt squared. I left off the prime, and I converted from the prime to the dx dt and dy dt notation, because you're going to commonly see this. You'll commonly enough see this too. Okay, so what this represents is our density, what this represents is our length, and that's integrated from A to B. Okay, wanted to check time, we're doing okay. The mechanics depend on the specific parameterization, okay, and that's pretty much all there is to it. Once you have the parameterization, you're going to be able to get this expression, and if you know your density function, you're going to be able to get this expression. And then hopefully when you multiply this by this, you are able to integrate it with respect to t. But whether you can integrate it or not, this integral will represent the total mass of this object.